Yeah, we did like. Okay, so the first question asks us, we have this system right here, bent bar. It is angularly rotating at 0.3 radians per second, and then it gives the dimensions, and it wants the magnitude of the velocity at this point B. So let's draw it. I'm going to call this point O, which is the hinge essentially. This is the H value. This is the L value, and this is point B. So, sorry. Let's define an initial frame of reference around point O. So we'll have this here. This is point O. This is the I hat. This is the J hat, and we'll call this I. Okay. So I want the velocity over here. So from physics 1, we know that velocity is equal to r, distance from O to B, using the initial frame as reference, times omega. And since omega is going to be constant throughout this entire body, we don't have to worry about omega here, or something like that. We just have to calculate the distance from O to B. So now we can do that by using Pythagorean theorem. So r is equal to square root of h squared, which is 0.3. So I'm going to call this ROB. 0.3 meters squared plus 0.7 meters squared, which is L, and this gives R to, yes?
So the velocity equation that you have, so it's like a vector on the left-hand side and there are two vectors on the right-hand side. So there has to be some kind of operator in it, right?
I believe this actually should not be a vector.
Actually, you're right. So remember the formula that we have for the velocity. So
yes.
Velocity of a point.
Oh, it's crossed. Yeah.
So
I'll do cross.
It should be the other way around, or you can put a minus sign because it should be omega cross r.
Omega cross r. Okay, so I'll just put a minus sign right here.
And I urge you to use the notation on the left-hand side for which points velocity you're looking at as well.
Velocity at B. Okay.
So here we have just one body, so it doesn't really matter, but just to be going with the flow in terms of notations, you can also mention the angular velocity of which body you're looking at, so you can give the body a name.
Alright, so let's call this body A,
Yeah.
and we'll call this right here. Okay. This turns out to be 0.762 meters, R OB, and this is in this is the magnitude. So we'll call this that. So
put that on the equation above as well. Magnitude.
yes. There you go. So now we can get VB to be, since we took the magnitudes, and because the angular velocity is perpendicular to the magnitude of the r vector, because the angular velocity is in the k hat direction, we could just multiply them together because the sine of theta is cosine of theta is equal to 1. Right? Or is it sine of theta? No, sine of theta for cross product. So sine of theta is equal to 1. Yes. So we multiply r, which is 0.762 meters, times, we have angular velocity is 0.3 radians per second, which goes to be 0.2285 meters per second.
So you missed this sign.
I missed a sign?
I mean sine theta.
Oh, yes. Here, let me rewrite this. So this is R, OB, omega A, both of them with I, sine of theta. Theta is equal to 90 degrees, and sine of theta is equal to 1. So we can ignore this whenever we're multiplying. Well, we could just multiply by 1, and then that gives you 0.2285 meters per second.
Magnitude of
Yes.
sorry for being picky, but just wanted to get everything consistent. Thanks.
Okay, it's on the board. Okay, so this question first asks you to find the velocity at point D. At point B, no, on the rigid body B2 at point B. So to do that, we use this equation. So VA is 96.2, and then the angular velocity across the distance is IJK 0, mega 2, 4, 10, 0. Because this is because this is like the distance of B with respect to A, the distance is wait, do I have that backwards? Huh? It's like
4 and 10.
Yeah, 4 and 10.
Is it right in the order?
Huh?
So which direction is your I and J?
I did this like a week ago. I have to remember. Yeah, they're backwards.
So you have arrows above all your vectors, just like you have an arrow above R, you have arrows above all the others as well.
Okay. Then this is equal to minus I. It's negative 4 omega 2 in the I direction minus negative 10 omega 2, and then in K direction. Okay. Yeah. I think so. So this is negative 4 omega 2 comma 10 omega 2 comma 0. What did I do? Okay, yeah. Okay, and then, so this is 96.2 minus 4 omega 2 comma 10 omega 2 comma 0. And then this is 92.2. Actually, no. Yeah. So this is the velocity on the rigid body V2 of point B. And then for part 2,
just to be consistent, I'd just like to add to the notation. So this velocity is of B with respect to the inertial frame. So here as well. And in this particular case, it's even more important than what Atharva worked on, that you have the angular velocity for the right body, because you have 3 bodies, B1, B2 and B3. So you need to specify which body it is for. And again, it's with respect to I. Okay? So just be consistent with this.
okay. Let me change that here too. Okay. And then for part 2, we need to find the velocity at point D with of B3, that bar. So we use this equation. And then, so BB is 96.2 minus 4 omega E2 is 10 omega E2, 0. And then the angular velocity of B3 cross R is 0, 0 omega 3, 0, 12, 0, 2, negative negative 12 omega B3. So now you add that to here.
The last row, you want to check the sign, because it's R from B to D.
Yeah.
So
Okay.
once again for the velocity equation, or if you put the pre-superscript I. That's for the R unit. Because this is the derivative is taken with respect to time. So R is, there's no derivative. R is just the position vector. So it's the same irrespective of which reference frame you're measuring it in. Whereas velocity and angular velocity are all time derivatives, and therefore you need to specify with respect to which.
Okay. And
so in that equation, it's a general vector equation irrespective of coordinate system. But when you start implementing it, you have the actual values that what she has in matrix, etc. Then you will need to specify.
okay. And now, so for part 3, we know that the velocity at D has to be 0. So the two components of the velocity are 0. So now we can solve for the angular velocities. So 0 in the I direction is equal to .2 minus 4 omega B2 plus 12 omega B3 the J direction is equal to 10 omega B2. And because this question only asked us to find the angular velocity, of B2, B2 is equal to 0.
Just show the J on the right hand side as well. The vector equation.
Okay, so we're working with the same system as the previous question. However, it's the question's asking, so they gave us if VA is 92.0 inches per second in the I hat direction, then find omega 3, the angular velocity component of bar B3 in the K direction. So first, our coordinate system, I'll just write it here. I hat and J hat. An inertial frame of reference. And let me draw the diagram here. So
So aesthetically pleasing.
So I've labeled points A, B, C, and they've given us that this is 8 inches, and then they've given us that this is 10, and they've given us VA. VA equals 92.0 inches per second. And then what is omega 3? Or this. Okay. So we can use the 2-point formula to solve for.
You need pre-superscript I on both.
Oh yeah. Yeah. So first I'll use the 2-point formula with VA and VB, and we have omega B2 in between, and then we can use that with B and C to get B3. So VB equals VA plus 2. Oh, it's not our hat. Okay.
Once you put the k hat, you don't need a vector on omega b2 because now that's the magnitude.
Oh, okay. So I can leave this?
Yeah.
Okay. Should I still write I here or not?
No.
Okay. Okay. And
Notation.
yeah.
If you want, you can. You put the otherwise.
So
You're essentially saying that vector omega b2i, the magnitude is omega b2.
yeah.
Or whatever. You can even say just omega 2. Something.
So then RAB is just so we use this coordinate system right here. So 10i plus oh, this is 12 inches by the way. Sorry. 10i plus 12j minus 8j equals 10i plus 4j. So we can say that that's RAB, and then we've got VBI equals right here because that's the velocity here equals 92.0 I plus WB2 K hat time cross product with 10I plus 4J. And doing the cross product here, we have omega B2 and then 1040. So if you do that, you get negative 4 omega B2 I plus 10 omega B2 J. So I put that here. You get VBI equals 92 minus 4 omega B2 I plus 10 omega B2 J. And then we know that the J, so we know this equals this, but we also know that this requires omega B2. So we know this part is 0 because there's no J component. So we can say
assume that VB has only an I component.
yeah, okay, yeah. So that's what I did. I'm not completely sure how else you would go.
You should keep it general and then let the vector equation decide, because from each equation you get essentially 3 equations, right? So in this case the K equation is trivial, but you would get the I and J equations anyways. So you will also be marching from the other direction. So you will essentially reach B from 2 paths, right?
Right.
From A and from C. So in either case you can get that. So I'm not saying it's wrong, it's in fact true in this case that it has only an I component.
Okay.
But at this stage we don't know.
Yeah, that's true.
Right?
Yeah. So what should I write J hat there or what? Or VB J hat?
Yeah.
Okay.
You would have a VBI and VBJ to start with. And
Yeah.
then you will show that VBJ is equal to 0.
Oh, okay, because I'll have two equations.
Yeah.
Oh, okay, okay, that's fine. Yeah. So I'll just write VBJ. I'll write this in. So then we have, yeah, so we have 92 minus 4 omega B2 equals VBI, or VB, because I'm just talking about the magnitude here, and then we'd have 10 omega B2 equals VB as well.
No, so you had that subscript now. And J, that's right, because you have, so these are, the magnitude is VBI, and
Yeah, this one, it's not.
so this is VBJ. So these are scalar quantities, which are the measure numbers along I and J.
Yeah,
So both are unknown.
yeah.
So you would have this as I and this is J.
Oh, okay.
It's not a unit
Yeah,
vector,
yeah,
it's
yeah.
just
You're
a
right,
subscript.
you're right.
Scalar.
Okay. So then, can I use cosine? Should I use cosine and sine with I and J? With it?
Not necessary right now, because this is just unknowns. You have to get to them from the other direction as well.
Oh, you mean continue from this one?
Yeah, yeah.
Okay.
Keep those equations aside and then.
Okay. Yeah, I can do that. All right. So we have VC equals in the VC in the inertial frame I equals VB plus omega B3 K hat cross R BC. R BC is just negative 12J. So, and we know that, okay, here, I'll just write the next line here. So RBC equals negative 12J. And then we can cross these two. So we have VCI equals VBI plus so if I do the cross product here again, you'll get 12 omega B3J. So then, right here, oh, I, yeah, sorry. So then you have I here because V, or wait, one second. Yeah, so you have whatever VB is here, VBI plus VBJ plus this equals VC. So we have VC equals where we're at here. Okay, and now we have now we have an equation for VC and vectors. Oh wait, I don't need these because it's a hat.
But you need a subscript I for VBs. The two VBs are not the same. VBI and VBJ. They've already derived them.
Oh, right here you mean. Okay. Okay, so do I, okay. Well, I'll just have it. So. Okay. So now we have this equation and these two. Let's see. One second. Oh yeah, can we use that VC equals 0 because in the previous one that's what it was said? So 0 equals VB.
Substitute for your VBIs and VBJs.
So what'd you say?
You can substitute because you already got your VBI and VBJ.
Oh yeah, so we can put these here, and then we have that 0 equals 92 minus 4 omega b2 for this, plus 12 omega b3. This is all in the I direction, and then plus VBJ, which is 10 omega b2j. Okay, and then huh? Yeah. So 0 equals the I, 0 equals the j. So 10 omega b2, or 10 omega b2 equals 0. So omega b2 equals 0. And then we can plug that in and solve for omega b3. Oh. So this equals 0. Yeah. And then omega b3 equals negative 92 divided by 12, which is negative 7.67, and it would be in the k hat direction, radians per second. Okay. Thank you. Yeah.
Can you erase the board, sir? Okay, so I'm just gonna first draw the diagram of important information because there's some stuff here that you don't really care about. Specifically, like the extra part of the bar is kind of useless in this example. So, alright. So, I'm gonna call this point A. Goes out over to point B. This goes down to point C. And this is going to go over to, I'm calling it D. I'm not going to use what they use. And then you have distances. So this is 0.4 meters. This is 0.3 meters. And this is 0.1 meters. And I'm just going to set up the frame of reference. So this is Y, which is J hat. This is X, which is I hat. This is going to be coming out of the page, so Z in the K hat. And then this is just the inertial reference frame I. And then you're also given that these, I'm going to call this AB is like body 1, BC is body 2. I know they call it B1, B2, B3. It's just the same thing. And so the information that we have that'll be useful is all the vectors from these points, and then these each have their individual angular velocities. So I'm going to write those out really quick. This is in this coordinate system, just negative 0.4 in the I hat direction. BC similarly is just going to be 0.3, negative 0.3 in the j hat direction. And then CD is just positive 0.1, the x hat direction. And then you also have all the angular velocities. So just put it here. The angular velocity of the first body is just in the k hat direction, and it's rotating counterclockwise, so it's coming out of the page in the k hat direction. The second one is also rotating counterclockwise. And then the final one is rotating clockwise, so it's going to be negative, and then they give you the values like 5.4 radians per second. Okay, so that's just the setup of the problem. And like all the other problems, we're going to use like the velocity of a point with respect to another point on a rigid body, except we're going to have to like propagate it in a way because we want to find the linear velocity of D. But to do that, we have to go from A to B to B to C to C to D. But before, there's a really easy way to do that. But I'm just going to write out the equations for each of those individually. So first for the velocity of point B with respect to A on this body, it's just EA plus 1 cross with RAB. And you also know that this is like a rigid point, it's not moving, so this goes to 0. Now for the second point, or the second body from B to C on that body number 2. None of these cancel out because you don't know any of those values just yet. And then the last one from C to D, this is going to be a little bit squished, sorry. Okay, so we have to combine all of these equations, and we have all of these values, but just to make things a little bit clearer, you could notice that this is the equation that we really want. We need the velocity of C, so we can just put this in here, and then we need the velocity of B, so we can just put that in here. And we know this is 0, so the velocity of D is going to be, so from this first component, this is VC, so it's going to be W1 cross R AB plus I W2 cross R BC, and then plus I W3 cross R CD. This is just allowing me to do all these in one step. If you do them all individually, you get this same expansion. And then so it's going to be, the first part is 0, 0, 5 cross with negative 0.4, 0, 0. The second part is 0, 0, 1 cross with 0, negative 0.3, 0. The last part is 0, 0, negative 5.4 cross with 0.1, 0, 0. And if you do all of those out, you get 0.3, negative 1.54, and 0, which makes sense. We shouldn't have any velocity in the k-hat direction. That's in meters per second. So that's the velocity of D, and the question wants the magnitude of the velocity of D, so just magnitude of I VD square root of 0.3 squared plus negative 1.54 squared plus 0 squared, which is 1.5689 meters per second.
Which marker did you use? That was good. This one. All right, so this is our system, and we have the velocities and accelerations of the two endpoints of a rigid bar in plane motion, and we have defined the magnitude of acceleration of point C. So I'll draw out the diagram. So, oh, and this is our coordinate system. Yes. All right. So we have this is 2 feet. And then okay, so first they gave us that AA is 1 square root 2 feet per second squared, and we have AA here as, if you follow the graph, it's I minus J. Now I can't assume anything, but if you do the once you have this, and then once you find the magnitude of this, it would be square root 2. So that would be the vector for AA. So I'll write it as, I'll write it as this. All right, square root 2 feet per second squared, and then that equals minus j hat. Okay, and then VA and VB they gave. So we have VA equals.
So the second equal sign, I think you need a bracket.
Wait, where?
Multiplying. Oh, sorry.
This is the wait. This is the This is the magnitude. That's the vector. So I'll just write the vector. It'll make it easier. I minus j. So then we have that's 4.7 feet per second. Oh wait, this is not the vector, or is it? No, it's the magnitude. My bad. Okay. Yeah, that's fine. I'll just write VA. Okay. And then VB equals 13.1 feet per second. And we have the first equation relating A and B. So VB equals VA plus omega. This would be omega across the angular velocity across the bar from A to B. So should I write AB here under it, or?
Whatever you want to call the bar.
Okay.
Because there's only one rigid body, so it doesn't matter.
Should I just leave it as omega?
Yeah.
Okay. Omega k hat cross R AB. And RAB is just here, so it's just 4 in the I hat direction, so it's 4I. And then we have VB and VA. So they gave us the magnitudes, but they also gave us the directions. This is just in the negative j direction, and this is just in the positive j direction. So we have VB as negative 13.1 j hat equals 4.7 j hat plus cross of this, and then I'll do the cross product right here. You get 4 omega j hat. So negative 13.1 j hat equals 4.7 plus 4w j hat. And then we can set these equal. Negative 13.1 equals 4.7 plus 4 omega. And we get omega equals negative 4.45 0.5 radians per second. And now that we found the angular velocity, we can use the acceleration formula between the 2 points with omega to solve for the angular acceleration. So AB equals AA minus omega squared RAB plus angular acceleration K hat cross RAB. And so we have A, which is just I minus J. Okay. Minus, we have negative 4.45 squared for omega. And then RAB is just 4I. Plus, let's take the cross product here of JK. So we have angular acceleration. So that's just in the K direction. And then RAB, which is just 4I. So, and that equals 4 alpha in the J direction. So I can write that 4 alpha J. Yeah. And then if we square this, multiply, just simplify this out, we get AB is equal to negative 78.21 I hat minus, or plus 4 alpha minus 1 J. Now, we have AB here with this ratio for the vector. So it's minus 3I, minus 4I minus 3J. So if I write what they've given me as, how do I write the singular form, or what they've given us here? Because I want to use the ratio. I want to use the ratio they've given us with this to get J.
Ratio.
Basically, they gave us, so we can we say that AB?
So you can get the unit vector along that, right?
Okay, yeah, the unit vector, that's what I
You
meant.
just have to divide it by its magnitude. So, and then, see, if you use 3 and 4, you have 3 down and 4 this way, right?
Yeah. So I was thinking I could use that ratio with this to get J, the J component, because this also has to have that same ratio here, right?
Okay.
So
What are you asking me now?
So I was thinking, asking how to like write that, but I was gonna use that since this is minus 4I minus 3J, and this is minus 78.2I plus something J. You can find that the J component is whatever the I component is times 3/4.
Yeah.
So we
you
know
can
that.
write it as the magnitude of AB times the unit vector along that. So which
Okay.
is of course instead of 3 and 4 you use 3 by 5 and 4 by 5, which is 0.6 and 0.8.
Okay.
So instead of 3 and 4, if you use point, and then just you can use the magnitude AB.
Okay, so for unit vector, I just go hat on top, AB hat, or
Yeah, you can actually write it, right? So because it is 0.6.
yeah, like right here. I'm saying the notation. I'm asking the notation, like this.
Yeah, it will be the magnitude AB times that unit vector. So which is 0.8 I minus 0.8 I minus 0.6 J.
Wait. 1 second. No, because we have so you have the I component as 3 or 4/5, and the other component, the J component, as 3/5.
Yeah.
So like this.
Because the magnitude then will be 1. That's what is the unit vector. Right?
Yeah. Like that.
No, that into. So your AB is equal to this times this is your vector AB.
Okay.
So vector AB is equal to this into
Into
magnitude of AB.
Okay. Okay. So then we can use that ratio to find that IAB, because if you just divide this out and find the ratio here, you can find it for J as well. So that AB will equal negative 78.21 I hat minus 58.66 J hat. And then we can equal out these to get angular acceleration. So 4 alpha minus 1 equals negative 58.66. So then we get alpha equals negative 14.41 radians per second squared. So now that we have omega and angular acceleration, we can use another acceleration 2-point formula to get acceleration at C. So I think you can do either AC or BC, but I did BC. So AC equals AB minus omega squared RBC plus alpha K hat cross RBC. And so we have AC, and then AB we just found here, minus 78.21 I minus 58.66 J, and then minus this squared, negative 4.45 squared. RBC is here, which is would just be negative 2I. And then we'll add the cross product again with these two. So we know alpha is just negative 14.41. So we have 0, 0, negative 14.41. And then we have negative 2i. So we have negative 2, 0, 0. And then you get 28.8 J. And then, yeah, you can write that here, 28.8 J. And then if you just add this all out, you get negative 38.6 I hat minus 29.8 J hat. And that would be AC, but we want to find the magnitude. So the magnitude is the square root of negative 38.6 squared plus negative 29.8 squared. So we get that is equal to 48.786 feet per second squared. Yeah.
So do you know which one was the good marker?
It's the same as
Okay, my question had a similar setup to some problems in the first section. However, the numbers were different. And this time we are trying to calculate the angular acceleration of B3 of this third beam. So we'll draw out the diagram, have the important information. So of course, this is the bad one. Okay. So we'll call this B1, this one right here, B2, and B3. And we'll call this, because B is already used, I'll call this point C, this is D, this is E, and this is F. They gave us, this is 24 inches. This is 30 inches. They had a ratio of 15:8, which means that this is also 30 inches. So this is 40 inches. This is 34 inches. And this is 16 inches from point
It's
D.
a useful notation that I'd like all of you to use for the rigid bodies and the points to distinguish them. Whereas in your book they use a floral font, handwritten kind of a font. We typically use circles around rigid bodies, and for points we just leave them as they are. So we know which is a point and which is a body. We can easily distinguish while writing.
And then I'm going to define this inertial frame of reference over here. This is going to be the I hat direction. This is going to be the J hat direction. We'll call this I. And this is going to be out of the page is the K hat direction. Okay, so we defined our system. We have our given values. So we're going to have omega B1 is equal to 0.22 radians per second. And this is going to be in the K hat direction. And then this is alpha B1. I know it looks weird. Is going to be negative 0.12 radians per second in the K hat, second squared in the K hat direction. Reason why it's negative is because it's going clockwise. And our given equations. So I'm just going to write this generally. VC. We're also, before I get into the equations, we're also given that VC is going to be 0, which is also equal to alpha C. And then similarly, VF is equal to 0, which is equal to alpha F. I and I. Okay, so the given equations we have VB is equal to VA plus omega cross RAB. This is just a general form. I'm not specifying anything yet. And then this is alpha B is equal to alpha A plus, it's acceleration AB is equal to A, not alpha, my bad. Are you guys able to tell the difference between this or this? Should I specify a bit more? How about that? Yeah. Okay. This is alpha cross RAB minus omega.
Specify omega and alpha, which bodies it belongs to.
Yeah, so I'm just going to say the body between A and B. This is just a general equation.
But you've already given them names, like B1, B2, B3, you could use that.
So I'm just going to use the general equation and then plug it. So this is just for reference for later.
Okay, so I saw the same. Okay.
Yeah, just for reference. I'm going to rewrite it, everything, and then specify. These are not actual points on this. This is just general form. So we want the velocities. So let's do the velocities first, and then we'll do the accelerations. So velocities will go from C to D. So we have VD is equal to IEC plus omega B1 cross RCD. This is an I. And then this gets, so VC from we used before is 0 plus 0.22 in the K hat direction cross 24 inches in the J hat direction. This gives you a V is equal to negative 5.28 I hat inches per second. I believe I didn't miss any notations. D E, we'll go, actually before we go from D to E, let's go from F to E. Just because that's simpler. We want the point, we want this. So we're trying to like kind of converge to this point E right here, because we know that this over here, point F, is going to be 0. So we want F to E, which is IB is equal to IBF plus not theta dots B3 cross RFE. This gets you to 0, like we already mentioned before. B3. No. Let me plug this in. Oh, we don't know actually. So I'm gonna keep it like this. We do know that it is in the k-hat direction though. And then we have 40 in the j-hat.
Remove the vector on omega then?
Yes. And then we get negative 40, B3. This is in the I-hat direction. So we have this and this. Now we want to go from D to E. Oh gosh, I'm gonna run out of space. I'll just erase and rewrite. D to E. So we have VE. Oh, this marker is bad. All right, nice. D to E. We have VE is equal to VF plus omega 2. Oh, what am I doing? This is D. Omega 2 k hat, omega 2 cross R D E. And this is going to be equal to negative 5.28. This is VD. Negative 5.28 in the I-hat direction. Plus, and this is omega 2. We do not know omega 2. So we're just going to call this omega B2, sorry. And this is in the k-hat direction, so we'll take out the vector on top. Cross, and then the vector is going to be 30 in the I-hat plus 16 in the j-hat. And that's our R vector from D to E. This gets us to be negative 5.28I plus negative 16 omega B2 in the I-hat direction plus 30 omega B2 in the j-hat direction, which gets you to be
The line before that, you might want to use square brackets for the outer brackets, just to
yeah.
distinguish.
So that gets you to be negative 5.28 minus 16 omega 2 in the I-hat direction plus 30 omega 2 in the j-hat direction. Okay, and now we have two equations of VE. We have this one, we have this one, and then we have this one. So we basically set them equal to each other, and we basically get negative 5.28 minus 16 B 2 I hat plus 30 2j hat is equal to negative 40i omega 3i hat. So since there is nothing on the j hat direction of this this side of the equation, we assume that 0 is equal to 30i. So we assume that 0 is equal to 30 omega b2. Omega b2 is equal to 0, and then we plug that omega 2 is equal to 0 in this equation. We solve for omega 3. Omega 3 turns out to be 0.132 radians per second in the k hat direction. Okay, we'll keep this number in mind. Now we have to do the accelerations. Okay, accelerations. So from C to D, let's do that first. We have A, D. We know that the acceleration at point Z is...
R, you don't need the precedence.
For the acceleration at C, we know that's going to be 0, so it's going to be 0 plus... So this is negative 0.12 k hat cross 24 j hat minus... that's also going to be 0, so this entire term cancels out to be 0. We get A, D, I is equal to 2.88. I feel like it is not 0. Why did I say that? It is not 0. It is. I was thinking of a different thing. It's 0.22, and then this is 24 in the j hat direction. So this is 2.88 I hat minus 1.1616 j hat, and this is going to be in inches per second squared. Now we have to do the same thing for the other two. The other two, what is it? Bars, beams. So we'll do F to E first. F to E. A to A. Okay, this is squared. So AF we know is 0 plus alpha B3 cross 40 J hat minus, we found omega B3 from the last, when we were calculating velocities. This is 40J. This yields us to get negative 40, alpha B3 in the I hat direction minus 0.69696 in the J hat direction, also in inches per second squared. Okay, now we need to find dt. Okay. I'm gonna erase this part. Since it's all in my notebook anyhow. D to E. AD we calculated in the last part, which is 2.88I minus 1616J plus this cross product simplifies to negative 16 alpha B2 in the I hat direction plus 30 alpha B2 in the J hat direction. No, not that. And then omega B2, this is going to be 0. This is what I was remembering. This is 0 because we calculated that this was 0 in the velocity section. So AE is going to be 2.88 minus 16 alpha B2 in the I hat plus negative 1.1616 plus 30 alpha B2. This is a really long problem. And then J hat direction. Radians, no. Inches per second squared. Okay. And we set that equal to this expression right here. So this entire thing is equal to negative 40 alpha B3 in the I hat minus 0.69696 in the J hat direction. Okay, so we basically equate the J hats and the I hats together. Since this J hat doesn't have a variable, this one has, we can solve for alpha B2. Doing some simple algebra, alpha B2 is equal to 0.015 radians per second squared in the k-hat direction. Plugging this back into the I-hat components of both sides, we get alpha B3 I is equal to negative 0.066 radians per second squared in the k-hat direction. It makes sense. This thing is rotating this way, but it is like accelerating clockwise, so it makes sense that this B3 is also accelerating clockwise. And then we want the magnitude, so we take the magnitude, and since there's only one component, which is the k-hat component, it is basically just 0.066 radians. Oh wait, what am I doing? Radians per second squared. Yeah, that's it. I think if I use Cush's method of like combining everything into one equation instead of propagating all of them at once, it might have been easier, but
for acceleration, it's hard because the equation is so long.
exactly.
And also, you're doing it differently because you're like converging to a point rather than going one to the next. I don't know if you can do it that way.
Oh, that's true.
Okay, so we have a wheel on a plank with wheels, and the plank is moving to the right with velocity of 2.1 feet per second. The center of the circle is P. The radius is 1.6 feet. I need a new marker. .6 feet. Point Q is here, and the angular velocity is omega, and 1. Okay, so the question is asking us to find the velocity of point Q of the wheel with respect to this contact point. So I'm gonna call this point O. So first you need to find the distance of where Q is in relation to point O. This is Q, call this O. This is point P. Yeah, this is point P. Because like the question gives you this 1-to-1 ratio, we know that this angle here is 45 degrees. So this length here is 1.6 sine 45. this length here is 1.6, cosine 45, and this length here is the radius, because the distance from point P to point O is 1.6 feet. So the distance, so R of Q with respect to O is equal to 0.8405 negative 2.9614, 0 feet. And okay. So to get the velocity at point Q, we use this equation. Now the cross product is
Direction has to be from the point whose velocity you know to the point whose velocity you're trying to find out. So it has to be OQ. Or you can put a negative sign before you.
okay.
Yeah, but what you had there was Q. So if you want OQ, then you have to change this with the signs of OQ.
Huh?
You need OQ over here. You got QO. This was correct. So if you want OQ, you just have to put a negative, because they are a negative of each other. Are OQ and QO position vectors.
Okay. Yeah. So oh yeah. The angular velocity is equal to 1.3 radians per second. So 1.3.
I see how you work the right answer, because omega is also negative, so it's clockwise. So if they got cancelled, you would have got the right answer. So, that's right. Since this is negative,
Okay. This cross product comes out to be 3.84982, negative 1.47082. Yeah. So the initial velocity at point O is the velocity of this board that it's rolling on, but the velocity is going towards the left, so the velocity is negative. So negative 2.1 plus 3.84982, comma, negative 1.47082, comma, 0. This is equal to 1.7498 comma negative 1.097. Wait. Oh, I forgot to, yeah. This is wrong. 0927. Comma 0, and then so this is equal to velocity of q with respect to I, and the magnitude of VQ is equal to 2.063. It's a little off from the actual answer, but I'm assuming it's due to a rounding. Have the next questions.
Wait, I have to do a derivation. 2.4. Yeah. I can.
You can go ahead.
Oh, okay. All right. So basically, we want to derive the acceleration of this point P. We want to derive that its actual value is 0 in the I hat, r theta dot squared in the j hat, and 0 in the k hat. So we want to get this, and the way to do that is to use the equation for acceleration that we've been using. I'm just going to write it generally here, not applied to this scenario. So AP equals AQ plus omega of your body crossed with omega of your body crossed with r from Q to P plus the angular acceleration of your body crossed with r to Q to P. This is just generally, and now we're going to apply it to our scenario. So let's write everything out. So A to P is just A to P, likes, because, yeah. That's what we're looking for. So this first component, Q, is going to be, we're looking at point P with respect to C. This is going to be of C, the linear acceleration of C. This is going to be the angular velocity of this rigid body A. So WA, cross it with itself. And then R from Q to P. In this example, we're going from C to P, so it's going to be RCP. And then the angular acceleration of the rigid body, so crossed with, and then this same position vector again. Oops. Okay. So there's two ways to actually do this derivation. If you assume that the body has a constant angular acceleration, then this goes to 0. If you assume that acceleration is constant, basically, this will go to 0 and this will go to 0. But let's assume that it doesn't have constant acceleration and it is actually changing velocity. We know what all of these values are, just in general terms. So I'm going to write those down here. RCP equals, even though we don't have a value for the radius r, we know that it's going down in the j hat direction, so 0, negative r, 0. And we also know the angular velocity in general terms, so IWA. Since we're rotating clockwise, it's going to be going into the page, so negative k hat, so I'm going to use 0, 0, negative w. All right. We can rewrite acceleration as r times theta double dot. And if we're going in this direction, we're assuming it has some acceleration, it's going to be the I hat direction. Okay, so that's the first term. The second term, I'm going to start plugging all of these things in. So 0, 0, negative omega crossed with 0, 0, negative omega crossed with, and what's our position vector? 0, negative r, 0. And then these last two terms, this is, I'm just going to rewrite this as theta double dot. It's the same thing, but it helps whenever we come back to this. So once again, we're rotating counterclockwise. We're assuming it has some angular acceleration, so it's going to be the negative k hat direction. So 0, 0, negative theta double dot. And then the vector is the same that we have before, so crossed with 0, negative r, 0. Okay. And then whenever we start working all of this out, crossed with, this comes out to be negative. Okay, actually, this is kind of dumb. I've been using W. I'm just going to change those all to theta dot. So this is negative theta dot. When you do this cross product, you get negative theta dot r, 0, 0. So just in the I hat direction. And then whenever you do this cross product, you end up getting negative r theta double dot, the I hat direction. That makes sense. JK, it has to be in the I hat direction. So what happens is that this actually cancels out with this. So these go to 0 when you combine them. And then when you do this final cross product, you get theta dot squared times r in the j hat direction. And that's what you're looking for.
Okay. So, this part of the question asks us to find the S component of the velocity at point A. So first I drew the picture. The outer radius is 19.5 inches. The inner radius is 18 inches. The velocity at which is going, I'll just draw an arrow like this, is 85 miles per hour. So first, we need to convert this to inches per second. Inches. Inches per second. Yeah. And now to get the angular velocity, we divide this velocity by the inner radius. Comes up to be 3.111 radians per second. Okay, and now to find the velocity at point A with respect to point B, we first need to find like the distance between these 2 points. So .5 inches. And then to find the velocity at point A with respect to point B, you do the distance between these 2 points times the angular velocity. Which is equal to 124.67 inches per second. However, the velocity of A is going this way, since the angular velocity is going this way. The velocity of A is going this way. So this is actually negative. So the velocity at point A in the x direction is negative 124.67 inches per second. Yeah. What parts do you want me to erase?
So just erase this. So mine is a very similar question. The system is the same. I'll just label some more points here. And basically they want us to find the velocity of E, the linear velocity. And so the wheel is rotating about point A, or on point A, so, or B, sorry, point B. So we know the angular velocity is going to be the same when we look at C and E. So just the linear velocities will be different. So we can use the angular velocity, we can set the angular velocities equal using the ratio for velocity and radius, and then we can solve for velocity of E. And they want this in inches per second, so first it's a good idea to convert the 85 miles per hour into inches per second. I did it the same way, dimensional analysis. And then after that, we have the angular velocity here, but you can also set this equal to the, basically the underlying principle is VE over R, or VC over RBC equals VE over RBE because the angular velocities are the same. And then we have this side right here. So then we can just do VE over the radius. Now for this one, instead of 18 inches, you have the added 19.5. So 18 plus 19.5 inches. So now we have the equation here. We can just solve for VE. And that's 3,116.67 inches per second. Yeah.
We can continue after lunch. Just 2 more questions. Quick. Okay, then we'll finish it. Okay. Oh, cool.
Okay, we had a bar over here. We have a circle, and then we have another bar. These two bars, wow, that was a bad circle. Pretend that's a circle. These two bars are moving, so I'm going to call this bar P. And this is bar Q. So this one is moving to the left, and this one is moving to the right, so I'll call this VP and VQ. So I'm going to only be dealing with magnitudes here, so we'll put the vectors and directions later, because most of this is going to be to the right or left anyhow in the I hat direction. I'll call this point C for center. This is the radius R. This is point S up top. This is point R, capital R down at the bottom. And then this is point B over here, and we want the magnitude of the velocity at point B. How do we do that? So we are given VP and VQ. So VP is going to be 5.7 meters per second in the right side, so I'm going to call this the I hat direction. Before we do that, let's define an inertial frame of reference. I hat and J hat. So it's in the I hat direction only, and then VQ is going to be 4.4 or 4.4 meters per second, well, negative in the I hat direction. That's the entirety of VP and VQ, and then the radius, little r, is going to be 0.2 meters. So essentially, we can redraw this to. Oh, by the way, the circle is rotating, because if you move this up top, then you get like a right motion up top here, and then a left motion up here. So it basically rotates, and we also assume that it's not going to slip. So we can rewrite this as. VQ over here, VP over here, this is C again, this is going to be omega. We have, and this is B right here. since it is not slipping and VP is actually moving faster than VQ, we have to assume that there is a translational velocity, and we'll call this VC. It is going in the right direction because VP is more than VQ, so basically rotates forward as well as, it goes forward as well as rotating. How to find this velocity? So we have two equations. Since they're not going to slip, we are going to assume that the components, the angular and translational components at this point is equal to VP. So we have VP is equal to omega R from C to, and this is point S, so C to S, sine of theta, and minus, right? No, plus, sorry. Plus VC. And then we also have VQ. Basically the same thing, omega from R sine theta, let's call this theta 1 and theta 2. And instead of plus, it's going to be minus VC. Reason why is because this is rotating that way, but the VC is going that way, so we have to subtract the values. Use these two equations. We set VP is equal to 5.7, VQ is equal to 4.4. 4.4. So we get, let's do VQ first. So this is going to be 4.4. And this is going to be 5.7. If you add them up together, these VCs cancel out. You get 10.1 is equal to omega CS sine of theta 1 plus omega RCR sine of theta 2. So we know that the angular velocity is in the k-hat direction. So this angle between the r vector and the omega vector is actually going to be 90 degrees. We said sine of 90 degrees is going to be 1. So we can just basically neglect this sine term here as well. We get, plugging in omega values, actually we don't know omega, sorry. We can plug in RCS and RCR, so we basically get 10.1 is equal to, RCS is 0.2, omega plus 0.2 again, omega, 0.4 omega is equal to 10.1, and that means omega is equal to 25.25 radians per second. And as we said already, it's rotating like this, so it's going to be in the clockwise direction. So technically it's in the negative k-hat direction. But I'm only going to be dealing with magnitudes right now. Basically, you can plug in omega again. You can take any one of those equations, plug in omega for here. We already know all the other values. We get VC is equal to 0.65 meters per second. And that's going to be in the I-hat direction since we know that VP is greater than VQ. Now we want the total, we want the magnitude of the velocity at point B. So we know that omega is going to be 25.25 clockwise. So if the instantaneous velocity is actually going to be pointed this way. So it's going to be in the j-hat direction. So we have VC, which is going to be staying constant in the I-hat direction. So we have, let's call this velocity at B. the magnitude is going to, the vector, sorry, is going to be 0.65 meters per second I hat plus, to get the velocity, this in terms of linear velocity, we basically multiply by r. So it's going to be WR sine theta again, but this is going to be the j hat. We know that sine theta is going to be equal to 1. We know what r is. That's from C to B, so I'll specify here. And yeah, just plug in all these values. We get VB is equal to 0.65 meters per second I hat plus 5.05 meters per second j hat. So this is the translational, and this is the tangential velocity. Take the square root of that, take the magnitude of that. VB is equal to square root, all that squared, Pythagorean theorem. You get 5.09 meters per second. Yes, sorry.
All right, they often say, last but not the least. This is very much the least, actually, because this problem was astonishingly simple. So it's literally one step. All right. This has a radius of 5. What is it? 5 inches. This has a radius of 2 inches. Wow, that is not centered at all. Okay. All right. So this is like some object that's moving at a constant velocity. I'll just have to set everything up. All right, and then I'm just gonna call this point A, point B. So if this is all moving at the same velocity, then you can like break it down and say, all right, this is moving at some velocity A, this is moving at some velocity V, so like VA, this inertial reference frame, equals VB. But that's not useful in this form. We are trying to figure out, the angular velocity of B. So we can rewrite these just by definition as theta A equals theta V RB. And you know every single value except for theta dot B. So theta dot B equals theta dot A RA over RB, which is 9 radians per second. It makes sense. Like the smaller wheel has to move faster to compensate for the speed of the bigger wheel. Yeah.
The way you drew it, I think, is a more challenging problem.
Yeah.
Basically, you did theta not R, theta dot R.
Half theta dot is 3.6, RA is 5, RB is 2.
Because you guys are tougher than me.
Forgot to mention I.
Oh yeah, last problem I just did it completely without I vector just to save time. I know that I gave proper notation and it's like, I think 2.2 just the length of the ball and the velocity and the acceleration.